Thank you for joining me today on my presentation for a vertical integration of picosatellites in an NGSS aligned curriculum. My name is Daniel Lee, and I am a high school teacher in New Jersey, and I will be presenting a case study as well as some of my own observations for this curriculum as well. This curriculum overview is designed for use in a secondary school setting that is applied in a non-traditional way. It is built upon the concept of allowing flexibility, and the end goal is to be able to have students invested for long-term retention, in particular aiming for college readiness that could potentially turn into careers in industry as practicing mechanical and aerospace engineers. So it attempts to address this big picture question. In the past 2 decades, education and STEM education in particular has had a large push to try and motivate students with a strong initial engagement into the subject, but then there is little done afterwards that continues to encourage students to remain engaged. And this is what one of the core aspects of the curriculum attempts to address in particular, this idea of turning external motivators into internal ones. So how is it that we can do that? Well, students explore iterative process of not just the engineering design cycle, but how it fits inside a potential science learning environment cycle that utilizes hypothetical deductive reasoning. And they do that through the picosatellites and long-term engagement eventually into CubeSats and everything in between. And they do this across a 4-year time period. And this 4-year vertical integration is meant to encourage students not participating in traditional extracurricular pathways such as robotics or science Olympiad as a way to increase equity in science through high value opportunities while decreasing rigidity. So some of our critical partners here. On the left-hand side are all the contributors to the ThinSat program out of Wallops Flight Center through Virginia Space, which is the national level critical partners that make ThinSats possible. And on the right-hand side is the local outreach portions that make up the participants in the ThinSat program, with Princeton University being a mentor school to our high school, as well as X in a Box, who creates the standard payload X-chip sensors for these picosatellites. None of that I covered today in our curriculum would be possible without the efforts of both groupings on the left and the right. So sincere thank yous all around to our commercial industry and institution partners. So now getting into the program goals. The club's overall goals are listed here, but 3 to pay attention to in particular include: 1, being able to mitigate student engagement loss across 4 years of high school by being flexible and accommodating to their needs each year. Secondly, creating communities that can support different levels of engagement into design and construction. And then finally, being able to facilitate a constant cycle between what kind of questions the students are asking and why they should care in the first place, along with enabling engineering designs that students create to answer those questions that they want to ask, and finding ways to then collect that data to either support or disprove their explanations. So here in our next slide, we have a couple of examples of images of each one of those phases. The ThinSat program is tiered in 3 ways, from an easiest way to a hardest way, and all 3 pathways will be explored here, but there are also 3 phases that are fairly consistent for each of those ways. In the images above from left to right, we have a phase 1 WeatherSat that is flown on a low altitude balloon launch, and in the middle we have the phase 2 engineering model as a way to create a satellite that models the primary mission of the picosatellite and is flown at high altitude up to the mesosphere. And then finally there is a phase 3 that results in an extreme low Earth orbit launch that exists as a secondary payload on the Northrop Grumman resupply missions to the ISS using an Antares rocket. So here you see on the image all the way to the right a 3-unit CubeSat dispenser that is currently outfitted to be able to launch the ThinSats, and each one of those ThinSats is 1/7 of the volume of a CubeSat for a total of 21 ThinSats. In our next image here, we have the space data dashboard, and here this is where all the data is downlinked from the satellites. This is a screenshot of the most recent resupply mission through the Antares rocket, and the highlighted portions are the student-made satellites, and the one in yellow is the high school, and the 2 in the light red are from our lead university, Princeton University, and they're 2 custom payloads, one of which we'll hear more about shortly. Unfortunately, on this mission, as you can see, many of the packets are blank due to stated power issues. None of the Princeton satellites were able to downlink either partial or full packets, but hopefully in the future launches will not have an issue of power. On our next slide, here we move on to the core of this presentation. The ThinSat program, as briefly outlined in the prior slides, is a process that occurs iteratively and each year. Each year, however, there is a focus point in particular. Each one of those pathways previously mentioned from the easiest to the hardest are explored across a 4-year progression, with the harder methods resulting in a skill set that is invaluable for students as they prepare for post-secondary schooling. And the goal of the ThinSat Club is to run parallel underneath at each curricular level with flexibility to allow students to join in at any point in time time in that process, starting with ThinSat Phases 1, 2, and 3. And this is just one example of how things might look for a student, but there are other choices that students can substitute between during the science and engineering elective curricula and still find success. So much so that if an engineering elective is left out, the ThinSat Club would be able to fill in those smaller gaps in between. So taking a look at freshman year in particular, students begin their courseload with physics, where really observation is key. Students are also developing ways to be able to then take the observations that they've made and then create explanations and then test those explanations while gathering data that allows them to conclude if a hypothesis or an explanation that they've created is supported or disproven in a systematic way. This way of thinking is based on what is known as an IL pedagogical structure and allows students to invest in their mission proposals by understanding those proposals deeply. In their engineering and science electives, they take Introduction to Fabrication and Rapid Prototyping with a focus in software such as Revit, Inventor, and Fusion 360. And in the ThinSat Club in particular, students are going through phases 1 to 3 in their first year, and with a focus in phase 1 as well as in mission proposal and development using those standard X-in-a-box sensors. The value in having this conversation here is that, one, students are able to handle this conversation with taking physics first in their science progression and can ask really great and meaningful questions to answer. And two, it also sets students up to explore potentially as an independent project at some point in the next 3 years. So some examples of student designed and developed mission proposals. These are examples of those missions that were a part of the ThinSat mission for NG15. These mission proposals came about based on students' abilities to ask good questions through their coursework taking physics first. These are all missions that are derivative based on the data that could be collected from the base sensors provided in the standard payload for the ThinSats. And here on this side, we simply have a weather satellite in preparation for a low altitude test launch, specifically a tethered balloon launch, collecting atmospheric data for model confirmation. And this one went to roughly about 100 meters. Now we move on to our sophomore year, where students are looking at this idea of being able to take chemistry with a focus on underlying mechanisms, and students make observations here and develop ways that allow reactions to occur as explanations for their observations based on a mechanism that exists either in nature or is created due to a non-equilibrium state attempting to go back into an equilibrium state. In their engineering and science elective, here they take microelectronics, which is an introduction to basic circuits and microcontrollers, and students create custom circuits to collect and read out data from sensors, starting with simple Arduino circuits and making their way up all the way to more complex circuits with the primary goal of becoming proficient in both hardware and software. Finally, in the ThinSat Club, students again are working through phases 1 to 3, but now have a focus in phase 2 in particular, working on payload integration onto custom TSL primary and secondary boards or a custom PCB based on mission proposal needs. Students at this phase are also working through data downlink from high altitude balloon missions, either as proof of concept or to analyze atmospheric trends that may exist based on their initial mission proposals. Students here at the core are really experiencing science and engineering now being interdependent rather than treating them as two separate pillars that create what we commonly refer to as STEAM. Here we have student developed sulfur dioxide sensor. Thanks to X-in-a-box for fabricating this on behalf of the students here at Montgomery High School. And in the second image, you have simply a basic circuit for base readings using only resistors values to offset to measure ambient SO2 levels, kind of as a 0 point for atmospheric sulfur dioxide readings. And now we move into our junior year. Here, students are taking biology to utilize their first 2 years within the science curriculum as a pathway to recognize that a majority of modern science is in fact application, with new observations coming about as a result of that application. In their engineering and science elective course load, they are continuing on with rapid prototyping for use in science fields such as biomechanical, environmental, and medical fields, while still developing and practicing their software and hardware applications. Finally, in the ThinSat Club, students are working through payload integration as well as exploring limitations caused by the different sensors that they developed last year, and potentially looking at completely custom packages having to be created. Students are utilizing those technical skills of breadboarding and soldering that they covered in microelectronics for rapid prototyping, and are beginning to really culminate all of those different courses that they've taken so far in their workload. So here we have a couple of examples of custom sensor integration that can either fly in phase 1 or phase 2. The first one is using a custom ESP to read out data, whereas the second image on the right in figure 9 utilizes a standard X-in-a-box CW01 payload to be able to read out that data. And in the next image here, we have a perf board designed by Princeton University, most recently flown on NG-15, part of the Katherine Johnson resupply mission as a secondary payload to the ISS through the ThinSat program. Its current form is designed to fit a ThinSat body as a TSL primary and secondary board replacement, and it uses an Arduino teensy to communicate with sensors through I2C and analog connections. And on the right-hand side, if you take a look, we have the TSL's payload board and secondary board. So the primary board here has its own sensors, but then the expansion connector allows for custom hardware sensor integration. The expansion connector attaches onto the secondary board to tie pins back to labels shown on the left-hand side of that secondary board, as you can see in the image. Now we move into our senior year. So students here now are looking at individual and independent research projects. In the science curriculum, they can take a class known as iSTEM or iSTEM-I, where students conduct an independent research topic and they choose and explore it in a novel approach, applying ideas from prior years of science, as well as through a project-based lens based on that student's interests or academic pursuits. And in their engineering elective course load, they design a portfolio that showcases their technical works as they prepare for their post-secondary education as well. And in the ThinSat Club, students who have successfully completed this junior year tasking at this phase would begin to look at fabrication of potentially custom PCBs using software like Fritzing or KiCad, and then a Bantam mill for carving and integrating onto a potentially PC 104 compliant CubeSat platform or a custom perf board that can integrate into the ThinSat hardware. Students at this point have also had opportunities for 3 separate launches through the ThinSat program as a whole. So again, referring back to that external motivator that has now turned into that internal motivator. So here we have a couple of images. On the left-hand side, we have an image of fritzing being used to develop custom B routes for export and use on a Bantam mill. And on the right, we have an actual prototype of that X chip that was developed. Currently, this one has an ESP and UV sensor tied together for integration onto a generic X chip payload as a 1x2 X chip. And here we have also the idea of what happens when we have quarantine as a measure. Instead of just rapid prototyping, it turns into rapid manufacturing, as it can feel like at some times. We have 3 different sensors that were rapid prototyped here. And in the back left hand corner, we have edge connectors. We have a 2x2 edge and then a 4 edge connector as well. And on the right hand side, we have student developed PCB boards that are PC 104 compliant and have redundant connections available through both tiebacks as well as X in a box connector nodes, so they can be flown in different configurations to maximize compatibility. And speaking of, we also have X in a box CubeSat configurations here that through the BS01 connectors are in fact PC 104 compliant. And currently these do not have a frame or housing structure, both of which are currently in development with our partner school through a CubeSat challenge set out by the US Department of Ed, where I will speak a little bit further on as well later on in this conference. So lastly, to just kind of wrap up some of the future work and yearly progressions that I want to speak on, one of the major goals of the program is to be flexible and to be able to adhere to student needs, with time not being the same factor that it might be in the classroom. Students are able to set their own criteria for what they want to accomplish in any given year, and they are the ones who get to determine how slowly or quickly they'll work through those items. The external motivator here, again, is that space launch that happens every year, and being able to find ways at the teacher level to integrate these things into the mandatory coursework is critical to the success of the ThinSats. The other thing we try to do is address talent loss in science and engineering due to students' personal circumstances, such as athletics or extracurriculars, as well as we found social economic disadvantages. So students who have younger siblings that they need to take care of after school, or who have to have a second job to support the family. And lastly, one of the big things that we try to do is recognize that science is in fact a collaborative endeavor rather than a competitive one, unlike the different clubs here at the high school, such as Robotics or Science Olympiad. The club in general has a high female to male ratio, in part, I believe, due to the nature of the ThinSat program. There is not necessarily a drive to quote unquote win, but instead that drive comes from the opportunity of being available to students to be able to take advantage of opportunities instead. Being a key pillar of the ThinSat program, the club naturally allows for a more inclusive and equitable platform to be able to retain those higher numbers overall. So what I want to do is just quickly go through and acknowledge a couple of groups and people that this work would not have been possible without. So thank you to Eugenia Ekina, Michael Galvin, Jason Sullivan, Joe Gargione, Edward Cohen, and the entire Montgomery High School Science Department. And then lastly, just a couple of those references for those of you who are interested. I will be available on the 29th during that Q&A session. So if you guys have questions or there's anything further you would like to follow up on, please let me know. Thank you for your time and for listening in on this presentation.